Invertibility, that is existence of inverse. When can you say that a particular square matrix possesses inverse? When can you say? All these things will be discussed under this heading, invertibility of a square matrix. Well, let capital A be a square matrix. A is said to be invertible if and only if there exists another square matrix B such that AB is equal to I is equal to B. Like this, we must be able to see and say that there is another square matrix B such that AB is equal to I is equal to B. And this matrix B, of course, if exists, is called inverse of A, denoted by A inverse, like that. Okay, so what do you mean by invertibility? When can you say that a square matrix A is invertible? AB is equal to I is equal to BA. My dear friend, you can recollect the definition of multiplicative inverse of real number system also. From this system, a real number A, a non-zero real number A is said to be invertible if there is another real number B such that AB is equal to 1 is equal to BA, if it is the case of number system. But in the case of matrices, A is said to be invertible if AB is equal to I is equal to BA. In the place of 1 in the number system, we have I in matrices. Moreover, to have multiplicative inverse in real number system, A must be non-zero. But here A must be non-singular. We see that of course. And in the definition, we have not included that here. But we observe that is a consequence, of course. Well, we shall now concentrate on that particular aspect in the next heading. Well, the next concept before us is A is invertible if and only if that A not equal to 0. That is, A is non-singular. If A is invertible, automatically that A not equal to 0. If that A not equal to 0, A is invertible. These are the two things that must be verified. These are a consequence of a logical statement, of course, very easy to verify. Let us first verify this part. That is, let A be invertible. Let A be invertible. Implies AB is equal to I is equal to BA for some square matrix. For some square matrix B. Consider that here, that AB is equal to that I is equal to that BA. Dat A into dat B is equal to dat I is 1. Dat BA is dat B into dat A, same. You see, dat A is a number, dat B is a number, isn't it? Product of two numbers is 1. It clearly indicates that this C is non-zero, that is non-zero, isn't it? If either of them is 0, how can the product become 1? Isn't it? Therefore, the step itself implies that A is not equal to 0. Of course, that B is also not equal to 0. So, if A is invertible, we have seen that that A is not equal to 0. Good. Conversely, we shall now verify this. Let that A not equal to 0. We have to show that A is invertible. How? Let us look at it. Now our turn is to assume that and prove this. Let that A not equal to 0. We know that A into adjoint A is equal to that A into I is equal to adjoint A into A. Right? We have verified. As det A is not equal to 0, I would like to multiply the entire equation with 1 by det A. What happens? A into 1 by det A into adjoint A is equal to I is equal to 1 by det A into adjoint A into A. Well, my dear, you name this sum B. What could you see here? AB is equal to I is equal to BA, isn't it? Therefore, A is invertible. Therefore, A is invertible. And A inverse is equal to 1 by det A into adjoint A. 1 by det A into adjoint A. We have. So, A is invertible means det A not equal to 0. Det A not equal to 0 means A is invertible. And from this discussion, we could have recollected a famous formula of A inverse. How to get A inverse? 1 by det A into adjoint A is A inverse. The next one. Properties of A inverse. First of all, if A is non-singular, then A inverse whole inverse is A. Next one, if A and B are two non-singular matrices of the same order, then AB whole inverse is equal to B inverse into A inverse. Of course, this is called reversal law of inverses. AB whole inverse is equal to B inverse into A inverse. Accordingly, ABC whole inverse is C inverse into B inverse into A inverse, like that. Like that. We have. Well done. One more thing. What do you mean by invertibility? AB is equal to I is equal to BA, like that. You must be able to have one matrix B. If such is the case, B is nothing but the A inverse. Therefore, A into A inverse is equal to I is equal to A inverse into A. A inverse into A. These are the immediate properties of A inverse, and we shall now obtain some more useful properties. We know that A into A inverse is equal to I. Take determinants on both the sides. Det A inverse is equal to det I. Det A into det A inverse is equal to 1. What is the determinant of the unit matrix I? 1. From this, det A inverse is equal to 1 by det A. Of course, this 1 by det A can also be taken as det A whole inverse. So, it is another useful and beautiful result. Det A inverse is equal to det A whole inverse. That is 1 by det A. Good. Next one. Another result. A into A inverse is equal to I is equal to A inverse into A. By taking transpose on all the sides, we have A inverse whole transpose is equal to I transpose is equal to A inverse A whole transpose. And we know the properties of transpose. The reversal of transpose is there. According to that, A, B whole transpose is B transpose into A transpose. I transpose is I. And this is A transpose into A inverse whole transpose. Well, my dear, let me name this sum B. B. What do you observe? A transpose into B is equal to I is equal to A transpose into B. What does it mean? Inverse of A transpose is B. Therefore, A transpose whole inverse is equal to A inverse whole transpose. A transpose whole inverse is equal to A inverse whole transpose.